Today, we're going to dive into the secret life of heat by looking at something called specific heat capacity. You're about to find out the hidden physics behind all sorts of everyday things, like why your pizza crust cools down way faster than that super hot cheese, or why a metal spoon in your soup gets hot almost instantly, but the soup itself seems to take forever to cool down. Okay, picture this. You've totally been there, right? It's a beautiful, sunny day at the beach. You hop out of the car, and the second your feet touch the sand, you're doing that frantic tiptoe dance all the way to the water. But then you get to the ocean and, it's so cool and refreshing. How in the world can the same sun make the sand feel like hot coals while the water stays so chilly? Well, that's the exact mystery we're going to solve today. All right, to get to the bottom of our beach puzzle, we first have to ask a bigger question. What even is heat? I mean, we talk about hot and cold all the time, but we're usually just talking about a number on a thermometer. To really get it, we need to go deeper, way beyond just the temperature. And here's the absolute key. A rise in temperature isn't just a feeling, it's a sign that an object's internal energy is going up. Think about it like this. When something gets hotter, it has literally absorbed and stored more energy. But what is that energy actually doing inside there? To see what that energy is doing, we have to zoom in. I mean, way, way in. We need to look at things from the perspective of the tiny little particles that make up everything around us. You know, when it comes right down to it, it's surprisingly simple. Temperature is really just a measure of movement. It's a way for us to track how much the particles inside any given substance are jiggling, vibrating, and moving around. And this gives you a perfect picture of what's going on. Over on the left, in the low temperature object, you can see the particles are pretty chill. They're just kind of vibrating slowly in place. But now, look at the high temperature object on the right. Whoa, those particles are going absolutely wild. They're zipping and bouncing all over the place. That extra energy we talked about, that's what it does. It gets the particles moving. Okay, so if heat just makes particles move, why does the same amount of sun make sand particles go crazy, but water particles barely speed up? Well, it's because every material has its own kind of hidden personality when it comes to absorbing heat, and that's exactly what we're digging into next. And this brings us to the star of the show, specific heat capacity. We usually just call it C. Now, the official definition is right there on the screen, but here's a simpler way to think about it. It's basically a measure of how stubborn a substance is about changing its temperature. If it has a high specific heat capacity, it takes a ton of energy to warm it up. Now, don't let the math scare you off. This formula is just our tool. It's the way scientists can put an actual number to that stubbornness we were just talking about. Let's really quickly break down what each part of this actually means. So C is the thing we're trying to find, that specific heat capacity. The triangle E, delta E, is just the change in energy we put in. M is the mass, how much stuff we have, and delta theta is the change in temperature we see at the end. It's a really neat little package that connects all these ideas. Let's look at some real-world numbers, because this is where it gets interesting. Just look at the difference here between water and aluminum. Water has a specific heat capacity of about 4,200. Aluminum is only 900. That means you need more than 4 times the energy to heat up the same amount of water as you do for aluminum. That is a huge difference. This all sounds great in theory, but how do we actually figure these numbers out? Can we measure them? You bet we can. And the experiments are actually pretty straightforward. Let's put on our lab coats. So, say you want to find the specific heat capacity of a block of metal. First, you'd get its mass. Then you'd stick a little electric heater and a thermometer into it. You check the starting temperature, then you turn on the heater for a specific amount of time, carefully measuring exactly how much energy you're pumping in. When the time's up, you check the final temperature, then you just plug all those numbers into our formula and boom, you've calculated C. And for a liquid like water, it's almost the exact same process. You measure the mass, but this time you put it in an insulated container so heat doesn't escape. You pop in an immersion heater and a thermometer, measure the start and end temperatures, track the energy you add, and then, you guessed it, you use the formula to find your answer. All right, let's reel it all back in. We've gone from the beach to the lab, so let's tie this all together and see what we've really learned. So, let's go back to that beach. We now know what's happening. The sun is beaming down energy on both the sand and the water. But sand has a very low specific heat capacity. It's not stubborn at all, so its temperature shoots up really fast. Water, on the other hand, has that super high specific heat capacity. It can just soak up tons and tons of that solar energy without its temperature changing very much. And that is the secret behind our beach mystery.
Okay, so now that you're practically an expert, here's a little puzzle for you to think about. If you were designing the ultimate coffee mug, one that keeps your coffee piping hot for as long as possible, would you want to make it out of a material with a high specific heat capacity or a low one? Give that some thought.